So today we will continue our discussion on the deadlock avoidance bankers algorithm itself. So in the bankers algorithm, we will see the second type of algorithm, that is resource request algorithm. So this resource request algorithm is the extension to your safety algorithm. Okay, and so the name resource request, why it has been given is like whenever a particular process it makes the request of the resources, this algorithm comes into picture. And this is whenever you have multiple instances of your resource types. Okay, so whatever right now you are seeing is the algorithm. So first in the step first what will happen is request of I, whether it is checked along with your need, whether the request, whatever the request a process makes for the resources, the count of those instances, whether it is less than or equal to the need of that particular request. If this is true, we'll come to this second step. In the second step, the same, whatever the process request the number of resources, it would be checked with the available resources in the system. If the request, whatever the process makes, if it is less than or equal to the available resources, currently available resources in the system, then only you can go to the next step or you cannot. So let us assume this is true, then we'll come to the step 3. So in the step 3, what will happen is first we will calculate the available resource. So currently available resources are your the available resource minus how many requests your process has made. That becomes your new available. Then you calculate the allocation. So allocation of that particular process is nothing but previous how many resources were allocated to it plus now how many new requests it has made. Now this addition of this, it becomes your allocation. And the need of that process still needs it, the process, it still needs some many resources, right? So that need is nothing but the old need, previously how much it had, minus your the currently or new request the process has made. So I'll give you an example. I'll traverse through the algorithm, then you'll understand. Okay, so the example is the same thing whatever we have considered for your safety algorithm. So by now you must know what is allocation, max, available, need, and how these numbers have come. And okay, I'll give you here this. I'll write A, it has 10 resource, B, sorry, resource A has 10 instance, B has 5 instance, and C has 7 instance. So whenever this has been given, so by looking into this diagram or this number, you might now know what are these things, like how these maximum or available, how this has been calculated. Okay, so again we have 5 processes in the system and we have 3 resources. The available or maximum resource instances are 10, 5, and 7. So this is the allocation and these are the needs currently available and the maximum. So now we will traverse through your algorithm. Okay, so whenever the situation like this is there, so we'll assume or we'll say the process P1, apart from this allocation and apart from this max, it has requested for the resource 102. That means it has increased its maximum need. Okay, so apart from the allocated resources 200, your process P1, say suppose it has again made a request for 102 resource instances. That means again it needs one more instance of resource A, 0 instances of resource B, and 2 more instances of resource C. Now according to our algorithm, first we'll check whether the request is less than or equal to need. Okay, so the request made by your process P1 is 102. Okay, whether this is less than or equal to the need of this resource. Okay, P1, what is the need of this resource? 122. So 122, this is true, right? 102 is less than or equal to 122. Now once this step is true, you go to the second step, and in the second step what you do, you check whether the request is less than or equal to the currently available resources in the system. So in the second step, you check the request made by that process is less than or equal to the currently available resources. What is currently available? 322. Okay, so you have to check for this condition. Again, this condition is true here, right? If this condition is true, you go to the third step. What you do in the third step? First, you'll calculate the allocation, right? Allocation is equal to allocation plus request. What is the current allocation of your process P1? It is 200. So I'll write here allocation is equal to the current allocation plus the request. Current allocation is here, right? 200 plus what is the request from your P1? It is 102, right? 102. So the new allocation value, it becomes 302. Okay, the current, or the new value of P1, it becomes 302. I'll write here 302. Fine. Next, you will calculate the available. I'll write here the available is equal to available minus request. Fine. What is available resources in your system? It is 332. So 332 minus what is the request from your P1? It is 102, right? 322 minus 102, that becomes 2, 3 and 0. Okay, this is 3. 230, this is the new available value. Then you will calculate the need. Okay, this is need. Need is equal to need minus request. These formulas are there in your algorithm. Okay, so what is the current need of your process P1? It is here, that is 122. 122 minus request. Request is 102 from your process, right? So the current need now becomes 0 to 0. Okay, so total you had 10 instances of A, 5 instances of B and 7 instances of C, which was the allocation here. But when the process P1, when it had made one more request for these many resources, then you have to find out all these things, the allocation available and need for that particular process, it changes. So once you have calculated all these things, now you have to apply the safety algorithm. I had told you, right? Resource request algorithm is nothing but your extension to the safety algorithm. So once you have done this, resource request algorithm, now you have to follow the safety algorithm for all the processes. Okay. So I'll not explain again the safety algorithm for this process. So what I'll do is like I'll directly give you the safe sequence. Okay. So if you want, you try out the safety algorithm for these resources. For again P1, make sure you take the new count only. Okay. Whatever we have found out here, right? You have to take the new count. Do not take this one 200, 332 and 122. You have to take this new value for the process P1, right? So I have already worked out this safety algorithm, and if you execute the process in this order, that is P1, P3, P4, P0 and P2. Okay, if you execute in this order, you try out the safety algorithms, you will end up in the same order. Okay, so this is the safe sequence for the processes in the system, and whenever the processes executes in this order, whatever the safe sequence is there, if it executes in this order, we say that our system is in a safe state. There is no occurrence of the deadlock. So this is about your deadlock avoidance. Okay, in the deadlock avoidance, we had seen safe state algorithm, then we had seen resource allocation graph algorithm, then we had seen bankers algorithm. In the bankers algorithm, we had seen two more types of algorithm, that is your safety algorithm and resource request algorithm. Fine. So if the question is asked for 10 marks in the exam, write a note on bankers algorithm, then what you have to write is like, write the data structures for that, that is what is maximum, what is available, what is need and what is allocation. Then you write the algorithm for the safety algorithm, safety, and then you write the algorithm for your resource request algorithm. Only these things algorithm means. Okay, do not or there is no necessary for taking this example and actually traversing through the algorithm. So this is it for your deadlock avoidance. Okay. Next topic, that is deadlock detection. So if a system it does not employ or it does not have a deadlock prevention or the deadlock avoidance algorithm, then a deadlock situation might occur or it may occur in your system. So in that environment, the system it has to provide or it may provide two things, that is an algorithm that examines the state of the system to determine whether the deadlock has occurred, or it can also have or it can also provide an algorithm to recover from the deadlock. So first we will talk about some algorithms that examine the state of the system to determine whether the deadlock has occurred. So in the deadlock detection, so first we will see a single instance of each resource type, then several instances of a resource type, and then we'll see the detection algorithm usage. Okay, so first we'll talk about single instance of each resource type. So here, if all the resources have only a single instance, that means a system has only one printer, not five printers. Okay, so that five it becomes the instances of the printer. But here in the single instance of each resource type, we consider that a resource has only one instance. So then we define a deadlock detection algorithm that uses a variant of your resource allocation graph, which is called as wait for graph. Okay, so it is wait for graph. Okay, so it is a variant of your resource allocation graph. So we obtain this wait for graph from your resource allocation graph by removing the resource nodes and collapsing the appropriate edges. So to say it like from resource allocation graph you have to obtain the wait for graph, right, in this single instance of each resource type. So how can you obtain wait for graph from this resource allocation graph is you have to remove the resource instances from your uh, resource allocation graph. So that means, say suppose if you have this condition p1 is requesting resource r1, but this resource R1 has been allocated to P2. In that case, if this is the situation in your resource allocation graph, now to obtain your wait for graph, what you have to do? You have to remove this resource. Then what you will have? You have P1 to P2. So this means P1 is waiting for some resource and that particular resource has been allocated to P2. So that is the meaning of P1 to P2 or this arrow from P1 to P2 in your wait for graph. Okay. So again, the edges, this edge P1, this edge to P2. So this exists in the wait for graph if and only if the corresponding resource allocation graph it contains two edges, that is P1 to R resource and R to P2. Something like this should be present in your resource allocation graph. Then only this can be written as this in your wait for graph. Okay, we'll see an example here. Suppose you consider this resource allocation graph, this one. Okay, so here you can see P1 is waiting for R1, but R1 is allocated to P2. P2 is waiting for R3, but R3 is allocated to P5. Then again, P2 is waiting for R4, but that R4 has been allocated to P3. P3 is waiting for, okay, here P2 and P3 both are waiting for R5, but R5 has been allocated to P4. P4 is waiting for R2, but R2 has been allocated to P1. So now this is your resource allocation graph. Okay, now you have to remove all the resources such that this condition should be true. That means there should be two edges, like from a process the edge should go to a resource and from that resource it should go to a process. If this situation is present, then only you can remove that particular resource and you can have a direct edge from or edge between the two processes, which will result in your wait for graph. So here we can see, right, P1, I'll write here, P1 is waiting for R1 and R1 is allocated to P2. Now remove this P1, then what you'll have? You'll have this one, right? P1 to P2. This presents. Okay. Then we'll consider this one, P2. Okay. P2 is waiting for R3, but R3 has been allocated to P5. Now remove this R3, then you'll have a edge from P2 to P5, which is this edge. Then P2, I'll write here, P2 is waiting for R4, but R4 has been allocated to P3. Now remove this R4, what will you have? From P2 to R3, you'll have an edge, which is this edge. Then P2 and P3, I'll write here, P2 and P3 are waiting for R5, but R5 is allocated to P4. Now remove this one. That will become these edges, P2 and P3 to P4. Then last one, P4 is waiting for R2 and R2 has been allocated to P1. Remove this R2, then what you'll have? You'll have an edge from P4 to P1. So this is your wait for graph, which has been obtained from this resource allocation graph. Okay, so a deadlock exists in the system. Again, we have to check for the deadlock detection, right? We have obtained the wait for graph, this graph, from the resource allocation graph. But how to detect the deadlock? It is same as your resource allocation graph. That means if your wait for graph, it has a cycle in it, then that forms a deadlock. Okay, so to detect the deadlocks, the system needs to maintain a wait for graph, and periodically it has to invoke an algorithm that searches for the cycle in the graph. Fine. So this is about your deadlock detection. The first one, single instance of each resource type. Okay. Next, we will talk about several instances of a resource type. So here we have seen in the last topic, we had seen the wait for graph, right? So that wait for graph scheme, it is not applicable to the resource allocation graph if that graph contains multiple instances of the resource type. So now we have to deal with the deadlock detection algorithm, which is applicable wherein we have multiple instances of the resource type. So we have to have a algorithm like same as similar to your banker's algorithm, okay, which we have seen in the deadlock avoidance, and we'll have different data structures, and then we'll traverse the algorithm to see whether we can use that particular algorithm in our several instances of a resource type to detect whether a deadlock is there. So in the several instances of resource type, as I said, it is similar to your banker's algorithm. You have again the data structures. Those data structures here are available, allocation, and request. Note that your need data structure is not there. Okay, so available here, it is same as your banker's algorithm. That means the available resources in your system. Then we have the allocation. Allocation is nothing but the number of resources that have been allocated to each process. Then we have another data structure called as request. That request, it is nothing but the request from or the current request from each process. So we have this one here, right? Request of ij is equal to k. That means we have a process pi which will request k instances of the resource type rj. So request is nothing but a process making a request for the resource instances. Remember, we do not have a maximum and need here in this algorithm. So those two data structures are present in your banker's algorithm. So here we have something called as request. Now, how we have to detect there is a deadlock, right? So this algorithm, it is similar, or the algorithm steps are similar to your safety algorithm. Only thing here change is like instead of in the safety algorithm we had need less than or equal to work, right? But here what we have, the only change here is here we will check for request. Instead of need, we will check for request whether it is greater than or less than or equal to work. Fine. So this we have to check. I'll not traverse again the same algorithm and detect the sequence of the process and all. So it is similar to your safety algorithm, only changes this one. So first thing what will happen is whatever the current available resources are there, that will be put up in a variable called as work. Then work is checked with the request from a process. So if it is true, then the work has to be updated. That means whatever the process has requested, those many resources have to be given to the process so that it will execute and finally terminate from the system. Fine. Next, we'll talk about the last algorithm, that is detection algorithm usage. So here, when should we invoke the detection algorithm is the question. Okay. So the answer for this question, it depends on the two factors. That is, the first one, how often a deadlock is likely to occur in your system, and the second one, if the deadlock occurs, then how many processes will be affected by the deadlock. So these two factors, it will decide, or it will give you the answer for the question when we have to invoke the detection algorithm. So if the deadlocks occur frequently, then the detection algorithm also should be invoked frequently. That means resources allocated to the deadlock process will be idle until the deadlock can be broken. Apart from that, you have the number of processes involved in the deadlock cycle, it may continuously grow. So the deadlocks occur only when, say some of the processes make a request that cannot be granted immediately. So then what can we do? In this case, the request may be the final request that completes a chain of waiting process. So if it is the extreme case, then we can invoke a deadlock detection algorithm every time a request for allocation cannot be granted immediately. So in this case, we can identify not only the deadlocked set of processes, but we can also, the specific process that caused the deadlock we can detect here. Next, we will study about the recovery from deadlock. So if deadlock occurs, how to recover from that, okay? So when a detection algorithm, it determines that the deadlock exists, then several alternatives are available. So one possibility is to inform that the operator that a deadlock has occurred and let the operator deal with the deadlock. Then, how to deal with the deadlock is like manual. Operator will manually deal with the deadlock. So another possibility is to let the system recover from the deadlock automatically. So there are two options for breaking your deadlock. One is simply to abort one or more processes to break the circular wait. The other one is to preempt or forcefully, take back some resources from one or more deadlock processes. So from the recovery from deadlock, we will see two more things, that is process termination and about resource preemption. These are the two ways how we can automatically recover from a deadlock. The first one here is the process termination. So to eliminate the deadlocks by aborting a process, that means aborting is nothing but terminating a process. So we use these one of two methods. Okay, so first one, what we can do is like we can abort all the deadlock processes. That means, so this will break the deadlock cycle, but it would be a greater expense. The deadlock process may have, they have computed for a long time, and the results of these partial computation, whenever you are trying to abort or terminate a process, whatever the process has done till now, the computations, everything has to be discarded, and after that again you will have to recompute it later. So this is the one way how you can, whenever you terminate a process, the causes, these are the causes, like you have to, whatever the process has done, you have to discard all. Okay, next one is to abort one process at a time until the deadlock cycle is eliminated. So this method incurs your considerable overhead, since after each process is aborted, a deadlock detection algorithm is invoked to determine still you have a deadlock in those in that graph. Okay, you have to understand here, aborting a process is not easy. That means terminating a process is not easy. Why? Because if the process is in the middle of updating a file, whenever this case is there, if you try to terminate, it will leave the file in a incorrect state or the inconsistent state. Or say suppose if the process was in the middle of printing the data on the printer, then what will happen if you terminate the process? The system must reset the printer to a correct state before printing your next job, right? So if the partial termination method is used, then we must determine which deadlocked process or deadlocked processes should be terminated. So this determination is again a policy decision similar to your CPU scheduling algorithms or decisions. Okay, so we have many factors while choosing a process that has to be terminated. like what is the priority of the process, or how many resources the process needs in order to complete the task, or how many processes will need to be terminated, whether the process is an interactive process or a batch process. So these all factors come into picture when you try to eliminate a, or terminate a process from your system. Next thing in the recovery of deadlock, we will see about resource preemption. So to eliminate deadlocks using resource preemption, what we have to do is, like, we have to successively preempt some resources from the processes and give those resources to other processes until your deadlock cycle is broken. So if preemption is required to deal with the deadlocks, then we need to discuss the three issues here, that is selecting a victim, rollback, and then starvation. So selecting a victim is which resource or which processes are to be preempted. We have to decide it here. So as in your process termination, we must determine the order of your preemption to minimize the cost. So cost factors may include your parameters such as the number of resources a deadlock process is holding and the amount of time process has. So these all things factors have to be considered while selecting your victim. That means a process or the resource which has to be terminated or which has to be preempted. Then we have rollback. So if we preempt a resource from a process, if we forcefully take a resource from a process, what should be done with that process, we have to understand here. So whenever you take back a resource from a process, it cannot continue with its normal execution, right? So why? Because it is missing some, which it is missing some resource which it needs, right? So we must roll back the process to some safe state and restart it from the state. That means, say suppose there is process p1 and resource r1 is allocated to it. You say suppose you have to take back, or you have to forcefully take back the resource r1 which was given to that process p1. So in that case, what you will do, you'll take back the resource r1. Now the process p1 cannot continue its execution. Why? Because it needed resource r1, but right now it is not having it. So in this case, it is in an unstable state, the process is in an unstable state, right? So you have to roll back or take back or discard some of the instructions which your process P1 has executed, and you have to make sure that the process is in a safe state. There is no inconsistency of data. Fine. Next is starvation. So starvation, here you have to ensure that how the starvation will not occur in the system. That is how you can guarantee that the resource will not always be preempted from the same process. We have to check this one, right? So there is no meaning every time you take the resource from the same process. So the different process has to be taken into consideration and the resource have to be preempted. So in a system where the victim selection is based primarily on the cost factors, it may happen that the same process is always picked up as a victim. So as a result, this process never completes its designated task. Here, the starvation situation will come into picture. So, we must ensure that the process can be picked up as a victim only for a small finite number of times. So, if suppose you have, you have process P1, P2, and P3, say suppose like this, and we have resources. Those are allocated to some resource. Okay. So based on the cost factor, we will select a victim which is causing the deadlock, right? So it has to be taken into consideration that every time the same process, say for example P1, every time the same process P1 is not selected as a victim and the resource from it is preempted. What will happen if that is done? Your process, this P1, it will never execute or it will never complete its task. So we have to make sure that the process can be selected as a victim. This process can be selected as a victim only for some finite number of times. So the most common solution is to include the number of rollbacks in this cost factor. How many times the process has rolled back? Whenever you have, preempted the resource from it, how many times it has rolled back? So based on that count, we can make sure that the process does not go into starvation. Fine. So this is about your recovery from the deadlock. And that completes your third chapter. Okay.